Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos that give a gentle introduction to vectors. And in particular, in this video I'm going to introduce vectors in 3 and higher dimensions. So we're going to talk about the basis vectors, and I'm going to introduce the idea of a column vector, and we'll talk about the length of vectors in 3 and higher dimensions. Now, it's all very introductory. In previous videos, I've spent a fair bit of time talking about the two-dimensional case for vectors, and the three-dimensional and higher dimensional settings are natural extensions. So let me share my screen with you and get started. Okay. All right, so vectors in 3 dimensions. Now, up until this particular video, we've been looking at vectors in the xy plane or in 2 dimensions. Okay, so we've had the basis vectors I and j, which are perpendicular to each other and point along the positive x and y axes respectively and have length 1. Now, if we add another axis to the setting, a z-axis, then it would make sense to have another basis vector. So we have a vector k, which points along the positive z-axis, has length 1, just like the other 2 basis vectors, and is perpendicular to the other 2 vectors. Okay, so it turns out that any vector, every vector in 3-dimensional space can be made up just by using the I, j, and k vectors, by stretching, compressing, flipping, and adding or subtracting these I, j, and k vectors. Okay, so let me talk a little bit about that, and I'm not going to prove it, but let me just give you a little bit of insight into that. So you see here, if I move out, say if my vector A is A1I plus A2J plus A3K, where A1, A2, and A3 are all numbers, then, you know, out here, you could draw this vector here. So this vector here is just A1 times the basis vector I. This vector here would be A2 times the basis vector j. In this picture, this j has just been stretched. And this vector here would be A3 times k, because this vector here has just been, again, sort of moved down here and stretched. So you add those up using the triangle law for addition. What do you get? Well, the first thing you would get when you add A1I plus A2J is you would get this vector here. And then you've got another triangle law. You would add this vector to this vector, and the triangle law of addition tells you that the sum of this vector and this vector is this vector, which is the vector A. Okay, so it's similar to the 2-dimensional case, but it's just an extra dimension. Extra dimension, extra axis, extra basis vector. Okay? Now, let's talk a little bit about the column form of vectors in 3-dimensional space. Well, here is the column form. It's just like the column form for 2-dimensional space, but you've got an extra element here down the bottom. Okay, and this can be decomposed into these numbers times the basis vectors. Okay, I is the vector 1, 0, 0, j is the vector 0, 1, 1, k is the vector 0, 0, 1. Okay, so as an example, let's consider the following column vector, 3, 2, 4. Okay, that's just 3 times I plus 2 times j plus 4 times k. Okay. All right, so that's it in a nutshell. It's pretty, I've done that pretty quickly because I've spent a fair bit of time in previous videos talking about the two-dimensional case. Let's talk about the length or magnitude of a vector. Okay, now remember when you talk about length or magnitude, if the vector is geometrically is this directed line segment, then the length or the magnitude of that vector is the actual length of the line segment. Okay, so we know that in the two-dimensional case, if I cover up that and that, the length or magnitude of a vector is just what you can see down the bottom. And if we add another coordinate or another dimension, you would expect it to just continue. And again, it's just Pythagoras' theorem applied over and over. So we want to work out the length of this line vector here, or the line segment associated with it. Well, what you can do is work out the length of this vector here just by forming this right-angled triangle. So there'd be a right angle in here, okay? And then you'd have another right angle in here. So you can work out the length of that by looking at the Pythagoras' theorem on this triangle down here, where the right angle is down there. And then you've got another right-angled triangle where the right angle is down here, again by using Pythagoras. Okay, so let's look up here and compute the length or the magnitude of this vector here. So if I wanted to compute the magnitude of that, well, you take the 3, 2, and 4, you square them, you add them together, and you take the square root. Okay, so 9 plus 4 plus 16. Okay. Oh, sorry, not 19, 9. Root 29, which is approximately 5.385. Okay, so that's a 9, not a 19. All right, so that's a little bit about the three-dimensional case and vectors in three-dimensional case, in the three-dimensional setting. Can you keep going? Yes, yes you can. So vectors in even higher dimensions. Now, vectors in higher dimension, things get very tricky to visualize. Now you can talk about your basis vectors or the unit vectors that are all perpendicular to each other, and they all have length 1. Okay, so instead of using I, J's, and K's, you're going to run out of letters, of course, you use these E1, E sub 2, E sub 3, etc. Okay, so this would be your E sub 1, this would be your E sub 2, these columns, this would be your E sub n, and you can, form any vector, any vector in n-dimensional space through a combination of these basis vectors. Okay, here the A1, A2, A3 up to AN are all just numbers. Now the set of these E sub j vectors are referred to as the standard basis vectors for Rn. And in particular, we can decompose every vector in Rn into what's known as a linear combination of these basis vectors. Okay, well, we saw that the magnitude or the length of a vector in 3 dimensions was this. You square all the A1, A2, A3, add them together, take the square root. Well, you can just continue that on for the n-dimensional case. Okay. Now, we'll be spending most of our time in the 2-dimensional space and the 3-dimensional space, but we will occasionally come into this realm as well. Certainly for applications, the 2-dimensional and 3-dimensional space are very natural settings. So that's a little bit of an introduction to the basis vectors in 3-dimensional space and vectors in 3-dimensional space and higher dimensions. If you have any comments or questions, post them in the comment section below. And in the next video, I'm going to be doing some concrete examples to illustrate all the ideas and kind of pull them all together. So I hope you can join me for that presentation.